All right, so we learned about something called the geometric mean. And the geometric mean of two numbers is just the product of the two numbers square rooted. Okay? You multiply them together, take the square root. Okay? As opposed to the arithmetic mean, which is where you add the two numbers and divide by 2. Okay, and the whole purpose that we have this other kind of mean is to average percent growth rates. This is one important application of the geometric mean, average percent growth. So you just take the growth factors, multiply them together, square root to find average growth rate. All right, so I think maybe we'll come back to this later, but this stuff is just a little interesting investigation into the geometric mean, but we don't really need to know all about this to be able to do the Huntington Hill method. So we'll come back to this if we have time. But the point of our little excursion into learning about the geometric mean is so that we can learn the Huntington Hill method. So I'll start off by saying Huntington Hill works very much like Webster's and Adams and Jefferson's in that we tweak the divisor. It's another method where you change the divisor until everything works out perfect. What's different, what makes all of those divisor methods different, is the way you round. So with Jefferson's, you round down. With Adams, you always round up. With Webster's, you round using that standard rounding method. 0.5 and above, round up. Below 0.5, round down. We're going to have a new rounding method here, which is totally different than any kind of rounding you've ever seen. Okay, it's not round down, it's not round up, it's not regular rounding. It's based on the geometric mean. Okay, so the Huntington Hill rounding rule, it says if the modified quota is below the geometric mean of the lower and the upper quota, then you round it down. And if the modified quota is above the geometric mean, you round up. So with Webster's, we have this consistent cutoff of 0.5. Above 0.5, round up. Below 0.5, round down. And that's the cutoff all the time. Now our cutoff is going to be moving, right? It's like a moving target. And you have to calculate the cutoff before you can round. And the cutoff is the geometric mean of the lower quota and the upper quota. So for example, let's say a state's modified quota is 32.68. First, you calculate the geometric mean of the lower quota and the upper quota. Okay, so the lower quota is 32, the upper quota is 33, the round down and the round up. Calculate the geometric mean of the two. Calculator, 32 times 33, and square root it. We get 32.496. Then we use that as the cutoff value. If our quota is above that, we're going to round it up, and if our quota is below that, we're going to round it down. So compare 32.68 to 32.496. 32 is bigger, so you round it up. It's above the cutoff, you round it up. So 32.68 is greater than 32.496. So we round up. So it's similar to Webster's in that Webster's, we never really think of it this way, but when you do standard rounding, you're taking the arithmetic mean of 32 and 33 and using that as your cutoff, right? Because 32 plus 33 over 2 is 32.5. Okay, so now instead of doing the arithmetic mean as the cutoff, we're going to do the geometric mean. Above it, round up. Below it, round down. So summary of Huntington Hill. We have to find a suitable divisor D. You follow the exact same flow chart we do for Jefferson's and Adams and Webster's. If your sum is too big, make D bigger. If your sum is too small, make D smaller. Using D as your divisor, compute each state's modified quota. And then each state is apportioned its modified quota rounded according to the Huntington Hill rule. So sometimes up, sometimes down, depending on the geometric mean. Same flow chart to find D. So here's an example. We have a small country of 5 states, A, B, C, D, and E. We're going to apportion, I left out D. Sorry. There's a D, D and D, sorry. So we're going to apportion 40 seats in this legislature using Huntington Hill. So it's often helpful to have a total column. So I'm going to add one in there. So as usual, we're going to start with a standard divisor. So standard divisor is total population, 400,000, thank you. Total population divided by number of seats. So 400,000 divided by 40 seats, which is 40,000, 10,000 people per seat. So 10,000 people per seat. So I'm going to divide 10,000 into each state's population and get the standard quotas. So 10,000, that means I'm going to move my decimal point 10, 100, 4 places to the left. So this will be 3.48. This would be 10. What? Am I doing it wrong? 10.4. I'm. Oh yes, no, I'm going to write 10.48. I'm not going to round them if I can avoid it. All right, 64,800, so that's going to be 6.48. And this would be 14.08 and 5.48. And when we add up all the standard quotas, we should get exactly 40 if we did everything right. Okay, so now I have to decide how to round these things. So the rounding is based on the geometric mean of the lower quota and the upper quota. So you don't have to write this all down every time you do this method, but in the interest of making everything really explicit, at least for the first example, I'm going to write everything out. So I need the lower quota and the upper quota. Okay, so for 3.48, the lower quota is 3 and the upper quota is 4. And for 10.48, lower quota 10, upper quota 11. 6.48, 6 and 7. 14 and 15. 5 and 6. Now what I need is the geometric mean of the lower quota and the upper quota, because this is my cutoff for rounding. Geometric mean of lower quota and upper quota. Okay, so I'm going to do 3 times 4 and take the square root. 3 times 4, square root, 3.464. 10 times 11 and square root, and I get 10.488. 6 times 7, square root, 6.4807. Basically, I'm keeping enough decimals so that I can compare which number is bigger, my standard quota or the geometric mean. So you might have noticed that some of the, like I wrote down 4 decimal places here, where all the other ones I kept 3. The reason is that if I only wrote 6.48, if I rounded this, I would have the standard quota and the geometric mean look exactly the same, when in fact this one's a little bigger. So keep enough decimals to be able to compare the two. Yeah. Yes. Yes, with Webster's and Huntington Hill, you are more likely to have the standard quota work outright, and there's a little less guessing. Yeah. Okay, so let's see, 14 times 15 square root 14.49 and 5 times 6 square root 5.477. So these are my cutoffs. Now I need to compare my standard quotas with the cutoff values. If the standard quota is above it, we round up. If the standard quota is below it, round down. So this is going to be my row for Huntington Hill rounding. Okay, so 3.48 compared to 3.464. Standard quota, is this above or below the geometric mean? It's above, so we round up to 4. Okay. 10.48 compared to 10.488. Is 10.48 above or below? It's below, so I round down to 10. 6.48, is this above or below my cutoff of 6.4807? Below, so I round down to 6. 14.08 is below 14.49, so we round down. And 5.48 is above 5.477, so you round up. So this goes to 6. Now add up your rounded values. So I get 14 plus 6 is 20, 34 plus 6 is 40, and I don't have to do any modifying of the divisor. It comes out perfectly on the first try. So it's so similar to Webster's, except the cutoffs are weird, right? Instead of having 0.5 be the cutoff, where 0.5 and above you round up, below 0.5 you round down, you have to calculate the cutoff in every instance. Okay, so it's helpful if you write down the cutoff in your table. Okay, so for comparison, why don't you apportion using Webster's method? So we learned this last class, and I'm telling you what divisor works so that you don't have to spend a lot of time guessing. Okay. I just want to see how it turns out, the final apportionment, compared to what we just did with Huntington Hill. Okay. So we know that the standard divisor doesn't work just because I told you what divisor to use, right? So we can just start with that. We know that 9,965 works, and it's a narrow range, which is why I just gave it to you, because it took me like 5 or 6 tries to get that one. So on a test, in a testing situation, I will either choose an example. Can you guys just wait till I'm done? Thank you. I'll either choose an example that has a pretty wide range, so you won't have to guess, like, there's 2 numbers that'll work, or I'll give you a hint and tell you what D works. Okay. All right, so if I do each of my state populations divided by 9,965, I get 3.49. So these are my modified quotas now. 104,800 divided by 9,965, 10.51. Oh, what did it? Oh, okay, great, thank you. 6.5. Great, thank you. All right, so you got to be careful not to round to the 10th place when you're writing these down, because when you're rounding to the nearest whole number, you just look at the tenths. Like, sometimes it's second nature to see 3.49 pop up on your calculator and write 3.5, right? But because we're going to be rounding to a whole number, we only look at the 10th place to decide how to round. Okay, so if you're going to write down, so it's good to write down 2 decimals and accurately, to avoid accidentally making a 10th place a 5. Does that make sense? All right, so then we're going to round, standard rounding. So this is going to be 3, 11, 7, 14, and 5. Standard rounding. 0.5 and above, round up. Below 0.5, round down. You add those together and you get 40. So 3, 11, 7, 14, 5. Is that what we got when we did Huntington Hill? Oh, a little different. A little different. This one got 4, 10 instead of 3, 11. And we went 7, 14, 5, and this one went 6, 14, 6. So the apportionments are slightly different in this case. So they are different. Okay. In general, do you think that they're going to come out more often the same or more often different? Different? Yeah, you think it's going to...
It seems to be like a little bit more leeway, more spread. It's not as easy as the standard rounding.
It's definitely not as easy, right? Because you have to calculate the cutoffs. But what, you think they're going to come off more often the same? How come? Yeah, the geometric mean, what we use for the cutoff in Huntington Hill, right? These are really close to the cutoffs in Webster's, right? 0.464 is super close to 0.5, and 0.488 is really close to 0.5. Here's 14.49, right? Webster's method would use 14.5 as the cutoff. So the cutoffs are actually really close, and this problem was really carefully designed to make it come out differently so that you could see that there is a difference, right? So more often than not, they are the same. Okay. The final apportionments will be the same. Because the Huntington Hill cutoffs are really close to the Webster's cutoffs. So in general, what do you think of Huntington Hill compared to Webster's? Yeah, sure. Yeah, it's harder to figure, and it gives you most of the time the same result. Yeah. So it seems kind of silly that we dumped Webster's and went with Huntington Hill, but we did.
How do we fix that?
Introduce a bill into the Congress. This one it was permanently set as the permanent method. Yeah.
About law. Everything's written in stone.
Yeah, yeah.
Nice. J's and E's, I love it. But I think if they're that similar that you waste legislation.
Yep. Well, I think what it can be different.
It's more accurate, and it keeps
What?
in Congress.
What?
So that
Okay.
so
So that is really important. By fixing something as permanent, it keeps them from fighting over this every 10 years, right? So if we just say, this is the method, stop arguing about it, and it's just as good as the other one, maybe it's like, leave well enough alone, right? But my personal feeling is that they hired a panel of mathematicians, right, to come up with the correct method, while they were using Webster's. And the mathematicians probably went, well, I mean, Webster's is pretty good, but we got to give them something else. I mean, we're mathematicians, right? So they came up with something else.
So they
It's just as good, but a little bit harder so that it looks complicated.
Yeah.
So doing the geometric physics is not more accurate.
It's not more accurate, no. And by more accurate, I mean, it's hard to say what we mean by more accurate. Like, more fair? Yeah, not really. It's still a little arbitrary, I think. Okay, so now I want you to try Huntington Hill on the island nation of Margarita.